Yeah, thanks so much for the invitation to speak here. I'm going to be talking about some ongoing work, thank you, Carolyn, about non-invertible chiral symmetry on the lattice. So let me just start out with a sort of brief introduction. So non-invertible symmetries sort of have played an important role in the study of quantum field theory in the last few years. And sort of their defining feature is that non-invertible symmetry, wait, do I have a laser pointer here? Oh, there we go. Okay. For non-invertible symmetry, the sort of defining property of it is that the codimension 1 defect of a non-invertible zero-form symmetry satisfies fusion rules that are not group-like. Okay, so if this was an ordinary invertible symmetry, there'd be no sum here. So there would be sort of group-like fusion rules, and in particular, each element would have an inverse, so the C times C inverse would fuse the identity. In the general sort of non-invertible context, that's no longer the case. So in particular, if you're interested in representing these symmetries as operators in some very concrete tensor product Hilbert space of spins or something like that, then you can't represent them as unitary operators. Unitary operators are invertible. These things are not. And that's unfortunate because we gain a lot of intuition, even in quantum field theory, from sort of using a lattice regularization and Hamiltonian lattice regularization and representing symmetries as unitary operators. So in particular, there's a notion of locality, which is very nicely reflected in the structure of quantum, unitary quantum operators on Hilbert space. Namely, you can represent sort of local operators as quantum circuits, or more generally, quantum cellular automata. And there's just a lot of intuition that you can sort of get about symmetries from such representation. So for instance, a 't Hooft anomalies, just as one example of certain symmetries, can be sort of encoded in the circuit structure of the symmetry representation. So it's nice to have these kinds of unitary representations on Hilbert space, and naively in this non-invertible context, we don't have it yet, just because these things are not unitary. So, okay, well, so it's not hopeless. It turns out that in many cases, for these non-invertible symmetries, you can indeed find representations, operator representations of the symmetries acting in this kind of tensor product Hilbert space. It's just that they're not going to be unitary, and in many examples people have found they're sort of close to unitary. They're unitary times projector. Okay, so they're almost kind of unitary and maybe some subspace of the Hilbert space. And doing that actually does sort of give you some intuition for some of these non-invertible symmetries. So for instance, for Kramers-Wanier duality, when you put it on the lattice, you do an operator representation, you see that there's some kind of implication with mixing with translation or extension by translation. All sorts of intuition that you can gain. So our goal for this talk is to do the same thing, sort of find the lattice representation, operator representation, for the non-invertible chiral symmetry in 3+1 dimensions. Okay, so this is, I'll review that in a few slides. But this, roughly speaking, corresponds to the axial U1 symmetry in something like QED, which we know is broken by this ABJ anomaly. But it turns out that there's a Zn remnant that survives as a non-invertible symmetry. And this is kind of an important example just because it's tangentially related to other results like the Nielsen-Minimia theorem, et cetera. So it's an interesting example, folks. So let me review that just so we're all on the same page. Actually, sorry. Let me start with the plan. So right, I'm going to review this thing that I just talked about, and just to give you a preview of what we'll do next is we'll construct in a tensor product Hilbert space. We'll construct a representation of this sort of Zn remnant, this Zn non-invertible symmetry, and it will act as some unitary times a projector. So not invertible, but not too bad. And it'll satisfy sort of the sort of remnant Zn fusion rules. Okay, and I'll tell you what the projector is. I'll tell you what the unitary is. And then I'll discuss, if I have time, some interesting relation to quantum cellular automata. Tell you what that is. Okay, so first off, let me just review this idea of non-invertible chiral symmetry. So we start off simplest setting in which, I mean, there's many different field theories, and in fact, I'll introduce a slightly different field theory that I'm going to be targeting in a moment. But sort of the simplest setting in which this arises is just the quantum electrodynamics in 3+1 dimensions. So you have a U1 gauge field, you have a Dirac fermion, and when you set the mass to 0, there's an axial U1 symmetry, which is well, it's not a symmetry because it's the corresponding current is not conserved. So the divergence of this current is proportional to F wedge F. This is the famous ABJ anomaly. So even though at the classical level this current's conserved, quantum mechanically it's not. So here I'm sort of following the standard presentation of how to, from this setting, construct a non-invertible symmetry. So one thing that you can do is, even though this axial current that I wrote down here is not conserved, you can attempt to recover a conserved current, at least in a setting where the spatial manifold is simple. If you just have it working on an R3, what you can do is you can sort of notice that the previous equation can be rewritten like this, and you can just kind of use this as your generator of, as your U1 generator. So you can write something like this. And in R3 at least, this is fine. This is a gauge invariant operator, and this is sort of a good representation of the axial symmetry. But it's no longer gauge invariant in more general spatial manifolds, in particular T3 torus. And so what people have come up with to sort of, write down a corresponding operator on more general spatial manifolds is sort of, first of all, to become a little less ambitious. So instead of trying to write down a whole U1's worth of operators, one just works at these discrete angles, 2 pi over n. And for for fixed n, these discrete angles 2 pi over n, you can write down the following non-invertible symmetry operator. Okay, so I'm not going to get into too much of what this means, partly because we don't really, at least I don't really have an intuitive understanding exactly what this means. I mean, I can sort of tell you what's in the formula. But roughly speaking, the way that this is explained is that this part here is a fractional quantum Hall state that lives on the defect. It's a fractional quantum Hall state that lives on the defect and generates this 1 over n. If you have an alpha with a 1 over n here, it generates this 1 over n ADA term. That's what it's supposed to be, and it's not invertible because you have this integral, so it's basically a sum of unitaries rather than unitary. Okay, so our goal was to sort of understand this by thinking about it on the lattice. Like, how do you actually represent this as a lattice? Yeah.
So when I say R3, is S3 also fine?
I don't know. Is this gauge invariant S3? Probably.
Yeah,
I think so. Yeah.
So then let's assume this A is globally defined on S3.
Okay.
Yeah. That kind of.
Yeah. But for me, so I'm going to be targeting this more general situation. So for us, we're actually going to be working on a T3 torus.
Okay.
So we're really targeting this. We want to write down this. Not this. Yeah. Okay. Right. So let me sort of outline how one would approach this by first naively trying to just forget the U1 gauge field. Let's start off with a very simple situation where there's no U1 gauge field. There's just the Dirac fermion. Okay, and let's just try to construct this axial current. Now, we have a formula for the axial current. You can try to put it on a lattice, some free fermion picture, but it turns out that that naive regularization doesn't generate a U1 symmetry. It generates an R symmetry. Okay? There's no quantized U1 charges. And one way of sort of maybe seeing why, or getting some intuition for why this is an R symmetry and not a U1 symmetry, is to think about the way that the symmetry, this axial symmetry generated by this axial current acts. Okay, so let's just take a state. Psi is a state, and specifically, it's a gapped state. Think of this as in the QED context. Think of this as or no, sorry, in the context of a single Dirac fermion. There's no U1 gauge field. Think of this as just a massive Dirac fermion. So psi is not invariant under this axial transformation. It's only the massive case that's invariant. And so if I act, the state will change. But now what I can do is I can act only in 1/2 of space, let's say. So this is space. On the left, I do nothing. On the right, I act with the axial symmetry. And so sort of the defining property, it turns out, of this axial symmetry is that when I act at the interface, I get something that has a non-zero U1 Hall conductivity. Okay, it's proportional to this parameter alpha. It's proportional to how much I act. So in particular, I think this is kind of familiar maybe if alpha is equal to pi, in which case this is like a negative Dirac mass term because this axial rotation just rotates Dirac mass term, and this is like a topological insulator, it's a trivial insulator, and this is half Hall conductivity in the natural units. This is 2 pi, then you sort of pump out an integer quantum Hall state. But that really, it turns out to be the defining property of this axial symmetry. And that's something we're going to target. Okay, so in particular, let's, well, let me mention some complications before we sort of proceed. So I mentioned that there's a U1 Hall conductivity when you sort of act with this axial symmetry on 1/2 of space. Turns out there's also a thermal Hall conductivity. Okay, so in particular, if you act with alpha equal to 2 pi, what you do is you get back the original state here. You get back, you still have the original state here, but in the middle you have an integer quantum Hall state. So something with non-zero U1 Hall conductivity and non-zero thermal Hall conductivity. And this turns out to be used in at least in our argument for why this is an R symmetry, because basically if this was a U1, sorry, if this axial current could realize an actual bona fide U1 symmetry on finite dimensional Hilbert spaces, this would lead to a contradiction because basically you'd have a commuting projector representation for a state with non-zero Hall and thermal Hall conductivity, and that's sort of believed to be impossible because sort of everything here lives in commuting projector land. There's a lot more to that argument than what I just sketched, but roughly speaking, that's what it is. So that's a complication. That's sort of an immediate complication. They're sort of stuck at step 0, just trying to construct even in the ungauged theory, just this axial current. But it turns out that ultimately this complication just stems not from the U1 Hall conductivity, but rather from the thermal Hall conductivity. Okay, and thermal Hall conductivity is related to the fact that there's a gravitational contribution to this divergence of this axial current. So space, if you have a space-time with non-trivial topology, there's this other gravitational contribution. Somehow we don't want that. We want to focus just on the U1 part. It turns out that simplifies the situation. So we don't want to consider QED. QED is bad. It has this. We want to consider a slightly different theory, which doesn't have this, which still has the blue, which still has the U1, but not the gravitational. Turns out that that's not too hard to do. There's another complication, which is not nearly as bad, which is just that the underlying Hilbert space here is fermionic. Even when you sort of gauge the U1 symmetry, you have QED. There's fermionic gauge invariant operators. It's not a huge complication, but like on the lattice, it's sometimes easier to work with bosonic Hilbert spaces rather than C2 graded tensor products of fermionic Hilbert spaces. So we'd like a bosonic theory. So it's still going to involve emergent fermions, but the gauge invariant operators should be, it's still going to involve emergent fermions, but the gauge invariant operators should be bosons. So
is this story related to the difficulty of defining a single chiral fermion on the lattice?
Yeah, sure. It's a single chiral fermion on the lattice on like a 1 + 1D. Yeah, I mean, I believe all these things are presumably related, maybe tangentially. So the theory that we're going to target is not a Dirac fermion, again with the U1 gauge field, but this slightly more complicated theory. Don't be scared by this. Basically, this is just kind of rigged up to ensure that we're working with something where this new axial current. So okay, so now there's 2 different Dirac fermions, psi 1 and psi 2. So there's 2 flavors. And there's also two colors. There's a color index which I'm suppressing and an SU2 gauge field that couples this color index. So it's a more complicated field theory. Still involves Dirac fermions. It also involves an SU2 gauge field. Okay, it confines at low energy, and who cares? It's let's say that we're studying at some intermediate energy scale. But the nice property, the way sort of the reason we rigged up this field theory is that it has these properties that we mentioned. It gets rid of the gravitational contribution, so this axial current has no gravitational contribution. Basically, the neutral Dirac U1 neutral Dirac fermion cancels the gravitational contribution to the anomalous divergence. It still has the U1 contribution to the divergence. So this guy's charged, this guy's neutral. And it's a bosonic theory. It's a theory where gauge invariant operators are bosons, basically because of this SU2 gauge field. Okay, you don't have to understand this field theory too well.
But psi 1, psi 2 both are SU2 doublet.
Correct. Yep.
Sorry, Lukasz,
Yep.
let me understand.
Yeah.
So the U1 chart, the U1 in blue, those are the U1 you are about to gauge.
Yeah, exactly. Yeah. Those are the ones I'm about to gauge.
And the JA current is not a current for them.
It's not a current for the blue ion. Correct. Yeah. This is the axial. Yeah, exactly.
So I'm sorry, I'm trying to read this. Are the d mu for psi 1 and for psi 2 different? Is that how-
No, they're both coupled to SU2 in the same way. So the d mu.
Oh, SU2.
SU2. Yeah. Sorry, I'm sort of overloading my notation here.
Yeah.
Yeah. But I'm not going to focus too much on this field theory. So that's why I don't want to. The main important property of this field theory is that if you now consider a gapped state in this sort of triply gapped state in this field theory, like just give the masses to Dirac fermions. Then acting with this axial current, acting with the unitary that it generates, pumps out not an interquantum Hall state, but a bosonic state, which has U1 Hall conductivity, but no thermal Hall conductivity. And in fact, if you do the 2 pi here, it pumps out the bosonic SPT of U1, so the root bosonic SPT of U1. And so the nice thing about that SPT is that it turns out that there is a commuting projector representation for that SPT. So it's sort of, it's promising. It's going to evade some of these no-go constructions. And so in particular, DeMarco and Wen sort of effectively constructed this current already. They interpreted it in a slightly different way in terms of a partition function in 2 + 1D. But essentially, you can just think about a matter Hilbert space, which is a tensor product of U1 rotors. So this is a Hilbert space, which is a bosonic Hilbert space. And it has a natural representation of U1 symmetry, just like think about an XY model. It's basically the Hilbert space of just an XY model. The U1 symmetry the vector U1 symmetry just rotates all these U1 rotors. It's kind of the simplest Hilbert space you can think of with U1 symmetry. Well, except that it has infinite dimensional side Hilbert spaces. And you can construct, it turns out, what is basically an axial current. So this is an expression. Now, there's kind of a lot going on in this expression. Maybe let me say a couple of words of what I actually mean here. So first of all, I'm imagining that there's a simplicial decomposition here of my manifold. So these sites V live at the vertices of some simplicial decomposition of my 3 manifold. Just live at the vertices. That's where our degrees of freedom live. But we have a whole simplicial decomposition. And moreover, I want to think of these phi's as real valued, okay? But the wave functions have to be invariant under this. So really they're rotors, but I want to think of them as real valued. And I'm using this notation that DeMarco and Wen sort of introduced, which is integer closest to, this kind of weird roof ceiling notation. Maybe it was ceiling roof, I don't remember, but okay, roof ceiling, which basically means integer closest to. So you interpret all the quantities here as real numbers, and this roof ceiling is integer closest to. So in particular, this is not like a continuous function of its argument, but that's okay. It turns out that that's not a problem. And then finally, you interpret all these things as cochains. So this is a 1 cochain. This is a 2 cochain. They're simplicial cup product, which, okay, so I'm also assuming a branching structure. I'm assuming everything that DeMarco and Wen. This cup product can be well defined. This is a 3 form. And so this defines a current or a charge density. And it's not completely trivial to verify that this expression, well, it is kind of trivial, but it's not sort of completely trivial to verify that it is invariant under phi goes to phi + 1. you need to subtract this piece here. Okay. So, okay, this might seem very complicated. Let me give you some intuition what this expression is actually doing, because like I just wrote it down. It seems kind of meaningless. So one thing that it does is if you consider a manifold with boundary, M3 is now a manifold with boundary, and you consider this expression, so plug in the JA that I had, and just consider this expression, just as a unitary operator acting on this Hilbert space. It's a diagonal unitary operator in the rotor, so it's very sort of simple to think about. Then the 2 pi I kills this part because this is just integers. The whole point of this is to make things integers. 2 pi I times an integer dies. So you just get the d phi times d integer d phi, which is a total derivative, which integrates out the boundary. And if you act on a sort of trivial tensor product state of rotors where all the rotors are in their zero angular momentum state, such as the wave function is just a constant, the function of phi, you pump out this wave function to the boundary. This is precisely the wave function of the 2 plus 1d u1 SPT that was identified by DeMarco and Wen. Okay, so this thing does what we want. That's how basically we sort of know that this is going to be a good U1 symmetry. It does what we want.
Question.
Yeah.
I missed one thing. So on a closed free manifold, if you integrate this JA in space,
Yeah.
and on that closed free manifold, does it give a U1 or R symmetry?
It gives a U1 symmetry. Yeah, actually, next slide. So it gives a U1 symmetry. On a closed manifold, this term drops out because it's total derivative. So now you have just integers. Yeah. And actually, there's a nice sort of appealing interpretation of what this means on a closed manifold with boundary. Like what is this expression? This cup product with this? It's like something cup d something. So we're very familiar with something cup d something. Like A cup dA is like a Chern-Simons term. It means that you can think of this, which is a one form, as some kind of a gauge field, maybe one gauge field, and this is kind of like a Chern-Simons term. So what is this actually doing? In a superfluid picture, like imagine that the state of the XY model is just some superfluid, it's this 3-dimensional, spatial dimensional superfluid with some vortices. It turns out that this quantity just computes the self-linking number of these vortex lines in superfluid. That's all it does. Because some integer, which is like the self-linking number. Okay, self-linking number is a little tricky to define, but that's the whole point of the branching structure, the simplicity of the composition. And sort of that's kind of hidden in this cup product that sort of incorporates self-linking as well. So yeah, this just computes linking number, and you can view this operator as just kind of, if you view the trivial insulator as kind of a being obtained from a superfluid by proliferating vortex lines, and just proliferating magnetic fluxes, then so it's in superposition of all configurations of magnetic vortex lines. Then this kind of imprints that phase, that e to the I theta times linking number onto that ground state. So it's kind of an appealing representation of this operator. Okay, so that's going to be our axial current. And okay, you might ask, like, okay, is it really like can I emerge that field theory that I mentioned out of this microscopic setup? And yeah, there's an argument that I can maybe, there's a sort of heuristic. Yeah, basically we believe it can be done. There's a heuristic that I can mention later. I don't want to get too much into it, but this is the defining property, and it satisfies the defining property. Okay, so now we want to move on. We want to couple to a U1 gauge field. Ultimately, the non-invertible symmetry lives in a U1 gauge theory, not just a system with a U1 global symmetry. So we want to couple to a U1 gauge field. So microscopically, what we're going to do is we're going to use the Land formulation of lattice gauge theory. So it's going to be lattice gauge theory coupled to matter. It's again, just for the ease of drawing, I drew a square, but really imagine a simplicial manifold and 3-dimensional, so like tetrahedron instead of squares. But edges, vertices, bases, so we have degrees of freedom living on all of them in this Land formulation. So matter fields, again, still real valued, live on the vertices. Gauge fields, real valued. But I'm not going to use lowercase a notation because like I'm just used to dynamical gauge fields being denoted with a lowercase a. So whatever was uppercase a before is now lowercase a. Those live on edges. And then there's, in the Lang formulation, there's an integer that lives on the faces that keeps track of, basically allows you to access monopoles easily. So the Hilbert space that we're sort of ultimately going to target is all wave functions of these variables, which are invariant, first of all, gauge invariance. So this is just the usual gauge invariance condition. And also invariant under this Land condition. So basically, if you shift A, so V is an integer valued one form. So it's an integer, associated with each link. And basically, the idea is that this is what makes the gauge field U1 instead of R. So you're allowed to sort of make shifts of the vector potential A on each edge at the expense of also changing this number n on like the various bases that join such. Okay. Yeah.
So you mentioned that this also is meant for higher dimensional things. So if you have a higher dimensional thing with a triangulation, are there data associated to higher dimensional, higher than two-dimensional?
No. In fact, it's a good point. So I'm going to be working in 3 dimensions, but this is all the data that I need. There's no data associated to a 3-dimensional. Yeah, but yeah, exactly. So, but I do want to work in 3 dimensions, but there's no data associated to tetrahedron to the highest dimension. So thanks. Yeah. So that's the usual Villen formulation. Okay. So now we have the axial current that I wrote before, but now we need to gauge it. We need to sort of write down its version. Yeah, in this gauge there. Yeah.
Do you suppress dynamical model?
Good question. So for now, yeah, let's for now suppress them. Later, I will allow n-fold monopoles, but for now, let's just imagine that no monopoles.
So you're setting Dn to be 0.
Yeah, for now. Later, I'll set it to capital N. You know, some integer multiple of capital N, but for now,
Okay.
0.
Because naively, I would have thought you would have to suppress dynamical models. Otherwise, Alan Bubakov will destroy the number.
Right, but I think you're allowed n-fold.
Yeah, but they're not dynamical.
Okay, fine. We'll see. Yeah, you'll see. Good. So okay, so right. So now, yeah. So how do we gauge this? How do we gauge this axial current? So one thing that we better have is this relation here, which is just that, you know, if I take this sort of if I take this naive you know, expression and evolve by 2 pi, I better get 1. Okay, so here there's no fraction 1 over n, so this completely makes sense, and whatever my gauge version of the axial current is, better satisfy this. I switched normalization slightly. I changed the normalization of A by a factor of 2 pi, and there's an additional factor of 2 coming from the bosonic Hall connectivity, but so now it looks like this. There was no 1 A over 8 pi squared here anymore. So what that tells me is basically the gauged version of this current better satisfy this, at least in the continuum. That's in the continuum. So on the lattice, you know, if I want to make sense of this expression on the lattice in order to eventually write down this JA, I have to find the Villen lattice version of this guy. And it turns out that there's a nice Villen lattice version of this Trans-Simons term, which is this. Okay, so why do I include all these terms? Let me explain on the next slide. Why do I want to include all these terms? So what properties does this have? Okay, so it's DAA instead of ADA. That's not a big deal. It's just up to a total derivative. It's the same thing. It's just more convenient. What are properties of this thing? So if I take the integral of this, so this is a 3-form, simplicial 3-form. If I take the integral of this or sum over a closed manifold, it's gauge invariant. Okay, so it's invariant under this. So that's good. We want that. Yeah, and so far dn is equal to 0. And it's also invariant up to integers under this transformation. So when you do this transformation, the change of this is by an integer, which means that the exponential 2 pi I is well defined, and this was shown in this paper. Okay, so that's kind of a nice expression that we're going to use to define our gauged version of the axial current. But by itself, it's not sufficient because, you know, this expression itself is not actually gauge invariant. It's only gauge invariant under the integral sign. And here, the expression is not invariant under this transformation. It's only invariant up to integers. To have sort of a well-defined local current operator, we need to actually have something that's invariant on the nose under both these transformations. Fortunately, that's not too hard to fix up. So it turns out that if you write this expression, so this is the most complicated expression I'm going to have in the talk. I mean, everything else is going to be interpretation of this, yeah.
Are you using D for both de Rham and the simplicial co-boundary? Because I'm a bit...
Everything is simplicial here.
Everything?
Everything is simplicial.
Oh, I'm sorry.
Yeah, well, sorry, maybe it's possible that, yeah, in the continuum, when I wrote like ADA in the continuum, that was de Rham. Yeah, I apologize.
No, that's okay. But so they're... So
from now on, everything's
so both A and N are 1 cochains.
A is a one cochain, N is a two cochain.
A two cochain, great. Okay.
Yeah, A is one cochain, N two cochain, phi is a zero cochain. So the only role of this is to this part here is basically an integer, and its role is just to make the whole thing invariant under this Volan condition. And this total derivative, its role is to make this thing actually invariant, both gauge invariant and invariant. The whole thing is gauge invariant and invariant under the Volan condition on the nose. So it's a good candidate for axial current. Okay, so that's just this thing, the axial current. Now, I did something naughty here, like I'm supposed to do this, but the whole point of the rest of the talk is the interpretation of this. So at least on an R3, this doesn't make sense the way I wrote it on M3, but at least on an R3, we want to construct something like this. Okay, so we've constructed this piece. Now we want this piece, and we're going to stick it with a 1 over n and exponentiate. So the claim is this. The claim is that basically we have everything we need. So the claim is that in this expression for this axial current, the piece that I wrote here is like the ADA. Okay, this is now the field theory ADA. So this is the Durham, sorry. But that's why it's in quotes. And this is the remainder. So this is the thing, this is J star J minus ADA. So this is the thing that we want to stick in here. Now there's an obvious problem with this. This doesn't work because of the 1 over n. Okay, there's an obvious problem. These pieces are not individually well-defined in the Hilbert space that I want. It doesn't work. So how do we solve this problem? Okay, so first, so the solution will be the following. We're not going to define it in. We're not going to define this operator in the entire Hilbert space, but rather just on the subspace invariant under this Zn one-form symmetry. Okay. So the magnetic Zn one-form symmetry, just over any two cycle, so it's a one-form symmetry. So it acts not on the whole space, but it acts. So the action is defined with respect to any closed two-dimensional surface, and the action just kind of imprints this phase. It's e to 2 pi I over n times the integral of n over that two-dimensional surface. This is a one-form symmetry. This is a new thing that I haven't talked about in this talk yet. It's a one-form symmetry. It's not a zero-form symmetry. But let's look at the subspace of states invariant under this one-form symmetry. Ultimately, it turns out that we'll be able to define a unitary. We'll be able to define this unitary operator in this Hilbert space of states invariant under this one-form symmetry. So what is this? This is just saying that the magnetic flux through any non-trivial two-cycle is a multiple of capital N. Now, if you just look at that expression that I have, it's still not well-defined in here. Like, if you just look at this expression that I have, the whole thing is well-defined, but the individual pieces, in particular this piece in yellow that I want, is not well-defined. So in this Hilbert space. So in particular, under the Volan transformation, it changes by an integer that's not a multiple of n, and then it screws you up here with a factor of 1 over n. So it just naively doesn't seem to work. So we have to do something slightly more clever. So here's the slightly more clever thing. So the first thing ultimately it will work, but the slightly more clever thing that one has to do is first define a different Hilbert space, which is just a scaled up version, scaled up by a factor of n of the original Volan Hilbert space. So this is like the Hilbert space of a charge 1 over n scalar coupled to a U1 gauge field. So basically everything gets rescaled by n. Not everything, but a lot of things get rescaled by n. So in particular, the field phi, the wave functions are invariant under addition of n, rather just integer addition. So these are charged 1 over n. So it's sort of well known that here there's no problem in defining a thing that I want, this non-invertible symmetry, essentially because little a gets rescaled by a factor of n, and so the 1 over n in front of it gets absorbed. Now there's an integer, there's no problem. So it turns out that both of those pieces that I mentioned of JA are well defined in this Hilbert space. This is kind of like a softening of the constraints. You're sort of relaxing the constraints under which you're demanding psi to be invariant. So things are well defined here, but it's no surprise that things are well defined here. Kind of, this is not the solution. This is just the first step. So yeah, so this is in particular, this piece is well defined here. Okay, so let's explore this Hilbert space a little more. So in this Hilbert space, Hn, it turns out there's a nice electric one-form symmetry, which acts like this. So it shifts the vector potential, it shifts n. So it acts, so in H capital N, wave functions are invariant under transformations like this, where V itself is a one cochain which is valued in n times the integers. But the one-form symmetry is it's sort of an additional action on top of that. So it's one where V is now integer valued, but dV has to be valued in n. Okay, so it turns out that this generates a Zn one-form symmetry. And if you're familiar with the language of one-form symmetries, it turns out that what this does is it basically measures the fractional charge of Wilson lines. Okay, if you act with this one-form symmetry, it kind of measures the fractional charge of Wilson lines. Okay, our operator commutes with this one-form symmetry. And it turns out that it actually has a mixed anomaly with this one-form symmetry. Okay, so there's some interesting structure between this unitary that we've defined, which is well defined on this larger Hilbert space, and this electric one-form symmetry. And roughly speaking, I don't have really a lot of time to get into it, but roughly speaking, this unitary operator acts as an SPT entangler, one-form SPT entangler in this Hilbert space. Okay, so in particular, if you look at the Higgs ground state, which roughly speaking, corresponds to condensing phi. So it's this superposition of sort of all integer values for A minus d phi, with the corresponding superposition of all integer values for A minus d phi. Then when you act on this with this non-invertible symmetry, you get this phase imprinted, which is just the phase of the so-called Walker-Wong SPT, which is well known to be a ZN one-form SPT. So
which Hilbert space is this psi naught?
This psi naught is in the Hilbert space Hn that I've called Hn, which is the the gauge theory, the U1 gauge theory, rescaled by.
So I'm confused. So that's functions of phi A and E. What is this?
Yeah, that's functions of. Yeah, so sorry, so it's functions of phi A and E, and so this basic psi 0 is a state which is supported only on configurations where this is an integer, and it gives equal amplitude to all those configurations. This is probably incorrect as technically as written, but
so R is the A phi A.
R here is A minus d phi. Yeah, so these are this is real, but what I'm saying is that I want this to be an integer. So it's wave function 0 everywhere except where this. This is kind of the Higgs. Yeah, this is what happens when you Higgs. So A gets locked into d phi up to an integer. So it turns out that acting with this, if you just do computation, acting with this thing, which is now well defined in this larger Hilbert space, gives me a so-called Walker-Wong symmetry for the Walker-Wong SPT. And so this has been this kind of wave function is sort of well understood. This is a 3D wave function. You can think of R's as if you think of R's as now just integer valued, even Zn valued. This is a wave function. N has to be odd here for even n, slightly more complicated. But this is a wave function of a so-called one-form SPT. So it's a invertible state. It's trivial in some sense. There's no anyons in this. If I just view this as a wave function, some wave function of a if I view the R as Zn valued variables and view this as some wave function of those Zn valued variables, this is the wave function of an invertible state. It doesn't support anyons. It doesn't have topological order in the 3D bulk, but it's still nevertheless non-trivial in the sense that it's a Zn in the sense that it's a non-trivial SPT under this Zn one-form symmetry, under the Zn one-form symmetry, which measures the
So should I think about Hn as a subspace of the original Hilbert space?
So Hn is bigger.
It's bigger.
Hn is bigger. So I'll tell you about the subspace inclusions in just a sec. So far, Hn and H are unrelated. They'll be related in just a moment. Hn is bigger. The original Hilbert space is just something we haven't touched yet. Hn is bigger. And now I'm just sort of studying this inside Hn, and there's this nice one-form symmetry. And I have this mixed anomaly.
So far, these wave functions are independent of little n.
No, this is bad notation. So yeah, sorry, yes. So far they're independent of little. Yes, exactly. They're independent of little n. We have this structure. Yep, sir.
So the range of R here is an integer,
Yeah.
but whether you can reduce that to like a mod n integer, so everything is finite.
Yeah. Right.
It's the same thing with the previous with the n. Whether this you know A and phi are kind of R mod Z.
Right,
so it's
right.
finite range.
Right.
Whether you can make n finite range, and they don't consider n having infinite range. That makes things kind of.
Yeah.
Whether say n from just a mod integer would be enough to formulate your theory.
Okay. I think it should be, but let's talk. Okay. So let's now with the structure let's look at the subspace of our Hilbert space, which is invariant under this electric one-form symmetry. Okay, so it's a subspace of Hn, which is invariant under this electric one-form symmetry. So it turns out that because things commute, this thing has a well-defined action in this subspace. I'm calling this subspace He, and it's a non-trivial QCA in that subspace. So quantum cellular automaton. So what that means is that it cannot be represented as a circuit. And that's basically because it acts as this non-trivial SPT entangler. If it could be represented as a circuit, then you would be able to create this SPT1 preserving this electric one-form symmetry, which should not be possible. Good. So we have this action in He, and this is almost what we want because this Hilbert space He is subspace of Hn. Fractional charge Wilson lines have been eliminated. That's sort of what this electric one-form symmetry does. It eliminates the fractionally charged Wilson lines. So this Hilbert space He has so it has charge and Tuft lines, and it has it's magnetic charge and Tuft lines, and it has only integer charge electric lines. Now, our goal is to really define this operator not in that Hilbert space, but in our original Hilbert space Hm, which is the original Delaine Hilbert space with the magnetic one-form symmetry. But it turns out that these are isomorphic, and not only isomorphic, they're isomorphism that this isomorphism induces a locality preserving automorphism of the operator algebra. So these are really kind of the same Hilbert space. And the intuition for this is that look, both these Hilbert spaces are kind of the same. They have Wilson lines which correspond to integer charges and n-fold magnetic charge monopoles. So they're kind of the same Hilbert space. So you can basically conjugate, whatever action you've defined in here, you can conjugate by this isomorphism and get an action here, and it's preserved locality, and it works. So that's basically the construction. So we take this expression, which is well defined on He, and we conjugate it into Hm. Okay. That's what we do. Now, the interesting thing to notice is that He is a subspace of Hn. This thing's a QCA on He. It extends to a circuit on Hn. It turns out that Hn is a circuit. It's a sort of no problem. But on now, if you view it in Hm is naturally a subspace of the original space H, and Hm just simply does not extend to all of H. It just doesn't. This operator simply, it's well defined here, but it just does not extend to here. Okay, as a locality preserving operator, it just doesn't. And in particular, if you try to extend it, the Hilbert space has a Tuft lines whose magnetic flux is not a multiple of n, and those are just not mapped to local operators. They're mapped to membranes. Yeah.
Can you remind us again, how is H sub f defined?
It is. Here. This. Yeah. Yeah. Okay. So, right. Yeah. So this is that expression. Okay, so this is work in progress. There's a lot that needs to be done. We don't have a paper out. So far I haven't even really connected to the field theory I wrote at the beginning. Now, we have a heuristic argument that this field theory that I mentioned at the beginning should be emergible out of this microscopic setting. Let me maybe just give a flavor for how that argument goes. And in fact, let me maybe not talk about the fully gauged context, but let me just talk about the setting without the U1 gauge field. Okay, so the setting without the U1 gauge field says that if I look at, maybe let me go back to my setting without the U1 gauge field. If I look at this axial current here, I should be able to write down a Hamiltonian on this rotor Hilbert space, which whose low energy dynamics realize this field theory, this complicated field theory that I mentioned at the beginning, which is invariant under this this symmetry generated by this star JA, this guy here, and in which that symmetry acts in the appropriate axial way. So how does one do that? It seems like a tall order, and of course we don't have a proof. We don't actually have a construction for how to do this, but there's this heuristic that one can use, which is basically that emergibility is kind of more or less equivalent to gapping. So to show that you can emerge out that field theory is kind of the same problem as showing that if I have a copy of that theory, I can gap it against my degrees of freedom here. So I can introduce some Hamiltonian that couples that theory to my degrees of freedom with respect to symmetry and gives a trivial gap phase. So this is sort of a well-known heuristic. Roughly speaking, like the way you argue is you introduce ancilla degrees of freedom, which in which you have an on-site U1 vector and U1 axial, and in which you emerge sort of two conjugate copies of the field theory that you want. And that's no problem because somehow all the axial violations cancel out between the two copies. So you emerge out two copies from ancilla degrees of freedom, and you gap out one of the copies against these degrees of freedom. So if you can gap out one of the copies against these degrees of freedom, then the other copy is kind of your emerged system. So the trick is really, can you gap out, if I give you a copy of this field theory, can you gap it out against these degrees of freedom while preserving this symmetry? While preserving the symmetry which acts like this on my degrees of freedom and like the axial symmetry usually does on the field theory. And to understand why to give a heuristic for why that should be possible, let's think about what goes wrong if you just try to do it in the field theory. So just even take, just for simplicity, let's just even take not my field theory but just QED. You introduce a Dirac mass term that breaks the axial symmetry. Well, let's try to restore it by quantum disordering the mass term. So take a superposition of all configurations of different mass terms which vary in space. So that's naively now restored the U1 symmetry, but that doesn't work precisely because of this Hall conductivity problem. So in particular, if there's a vortex in the mass term, what happens is that along the vortex line, the system is gapless. It has this quantum Hall edge state, and you're trying to take a superposition of gapless state that does not give you a well-defined gap state. It just doesn't work. So that's why a gapped state, that's a heuristic for why a gapped state to preserve the axial symmetry is impossible. But now, if you allow yourself access to these degrees of freedom, in addition to the field theory degrees of freedom, then basically you can cancel out this obstruction, this Hall conductivity obstruction. So if you imagine a domain wall between the Dirac mass term with sort of different phases, there's a Hall conductivity coming from field theory, but it's precisely canceled by the Hall conductivity coming from here. Well, okay, so now I have to do work actually in my field theory. So there's only Hall conductivity in thermal Hall, not a thermal Hall. And so there's no obstruction. So it turns out that now vortices are just, there's no obstruction to gapping the vortices. They are just gapped, and you can do this quantum disorder. Okay, so that's a heuristic. I mean, that's not a formal argument, but that's a heuristic that, yeah, somehow this should be emergible. Okay. I should also say that even n is somewhat more subtle as even n typically is, and it turns out that you can define this 1/2n rather than 1/n symmetry. Okay, so let me maybe conclude. So, what are some ideas for future directions? Obviously, tighten this argument that I just sort of hand waved through. maybe relax the condition on bosonic Hilbert spaces. Like I don't think this should be too hard, you know, replacing rotors with C2 graded, fermionic C2 graded rotors. And then you don't have to use this complicated field theory. You can just use the original. Well, you still have to cancel out the gravitational anomaly, but you don't have to have an SEH field. And then yeah, there's a question about you know, if you have a gravitational contribution to this anomalous divergence, like a single Dirac fermion, what about that? You know, can we, that seems harder to deal with on a lattice, just because this technology from DeMarco and Wen only sort of, well, it's as far as I know, this is, it works for SBTs, which don't have a thermal Hall, just thermal Hall response, just the U1 Hall response. But I don't know about no-go result either way. So. Okay, I think I'm done here. Let me conclude. Thanks for your attention.